Nowadays, with the electrification of so many sectors and particularly transportation, the demand for efficient and high power density electric drives has never been so underscored. Integrated motor drives that combine power electronics and electric machines in a single enclosure can certainly play a major role. However, such combination brings many challenges such as high temperature operation, increased electromagnetic interference, and packaging. The use of the best available technology such as wideband gap devices is crucial to meeting those targets. Hello everyone, we are the WEMPEC team at the University of Wisconsin-Madison, and today we are presenting high-performance integrated motor drive using wideband gap enabled current source converters. The combination of WBG devices with the dominant voltage source inverter has several challenges. For example, the presence of a fragile and temperature-limited DC-link capacitor. It has a challenging short-circuit protection and its output has a high DVDT and high capacitive leakage current. This topology is also susceptible to elevated common mode EMI and detrimental single-switch short-circuit fault. On the other hand, WBG current source inverter is promising to solve the discussed issues. This is because it uses a high temperature capable and rugged DC-link inductor. It has a natural DC-link short circuit current limitation and its output voltage and current are both sinusoidal. It also has lower common mode EMI as compared to the voltage source inverter.
As an overview, this hardware demo takes advantage of PM motor drive control technology, the WBG switches, and the current source inverter to form an integrated motor drive that has significantly improved performance metrics as listed here.
However, one challenge of conventional CSI in IMD application is its low efficiency due to the use of additional diode. In this demo, we propose to use hybrid bidirectional switch that has lower voltage drop. Along with new modulation schemes, we can achieve noticeably improved efficiency over 98%.
Common mode EMI is another important metric that needs to be considered. A common mode EMI equivalent circuit was proposed to obtain the common mode EMI in a fast and accurate way. The circuit was used to design EMI filters that make the CSI-IMD meet EMI standard. Such filters has little impact on IMD's efficiency and power density.
Thermal design is another important issue for IMD. In a thermal design, the main sources of heat are identified. The next step is the development of thermal model that includes PCB and fan airflow. The developed model was compared against the experiment for verification and tuning. The PCB configuration, including copper thickness and thermal via distribution, was optimized along with the required fan power. Here shows the designed hardware that is used to assemble the current source converter integrated motor drive. On the bottom, it shows the assembly process. The IMD's equivalent circuit is shown here that consists of both current source rectifier and current source inverter, both using bidirectional switch.
Here shows the CSI-IMD during testing. On the bottom left, it shows the close-up view of the CSI-IMD built using silicon carbide FET bidirectional switch. The current source rectifier is also integrated into the same housing. This shows the dyno testing of CSI-IMD. From the torque meter measurement, we can see that the rotor is running at 500 RPM. From the oscilloscope's measurement, we can see that the CSI-IMD delivers sinusoidal output voltage and current waveforms to the machine. The CSR stage is also shown to have sinusoidal input voltage and current waveforms, demonstrating the benefits of current source converter systems. In addition, new control algorithm has been proposed that has virtual resistance damping. With the new control algorithm, the motor's command tracking performance can be significantly improved. As we can see, by implementing the algorithm, the motor has now very fast speed up and speed down process, with very good torque command tracking performance. The rotor has also been sped up to 1600 RPM with 3 kW input power. The measured efficiency of the CSI-IMD is 98%. With a 3 watt cooling fan, the IMD's components are operated well within temperature limits. In summary, the fabricated CSI-IMD has demonstrated high power density, efficient operation, and high quality input and output voltage and current waveforms. All the achieved performance metrics significantly exceed state-of-the-art motor drive technology. We are also currently designing a new IMD version where the CSI is placed in the same housing chamber as the machine, aiming an even higher power density. A combination of forced air and the use of motor housing as heatsink was investigated for the thermal management. Finally, WEMPEC has consistently investigated integrated motor drives and wideband gap devices. This project takes advantage of the lessons learned from the past, but also provides useful learnings for subsequent projects that aim for higher power ratings to be used in traction and aerospace. Stay tuned for future wideband gap enabled IMD progress. Thank you for your attention.